In this work, we learn motion controllers by letting the character directly see the environment using depth perception. We demonstrate the practical benefits of our approach for different application scenarios. In existing reinforcement frameworks, the environment is explicitly parameterized. In the first comparison, we show the advantage of depth perception over explicit parameterization by building navigation controllers with a fixed number of obstacles in the environment. When there are only few obstacles, the quality and time of both controllers are still comparable. As the number of objects increases, the performance of the controller learned with explicit parameterization drops quickly. On the contrary, with depth perception, the learning performance is more robust with respect to the complexity of the environment. In this comparison, we show that learning with raw vision input suffers from the curse of dimensionality, but with the hierarchical state representation, we obtain better controllers within shorter amount of time. We visualize the depth perception of the character. In this case, the character can perceive 8 depth values from the panoramic field of view of obstacles, and we only visualize the dimensions used for decision making. Here, the resolution of the vision is too low and the obstacles appear to occlude the goal, so the character makes an unnecessary turn. Finally, the character sees a passage and walks through it. In this case, the character can perceive 32 depth values, and the resolution is high enough to allow the character to see the passage earlier. Higher resolution of depth perception allows the character to see even more clearly, but the learning time increases dramatically. With our approach, the resolution can be adjusted adaptively. As the character approaches the obstacles, higher resolution can be used to perceive the situation better. When the obstacles are out of the character's way, low resolution vision is sufficient for decision making. Our adaptive model achieves the best performance, obtaining better results from high resolution and faster learning from low resolution. Here we show the adaptive depth perception for the goal object. As the character approaches the goal, higher resolution of depth perception is used for taking more precise actions. An advantage of using depth perception is that the learned controllers can be directly applied to environments containing arbitrarily shaped objects. We generate several controllers, with each trained for obstacles of a specific shape, and evaluate the controllers in environments containing bars. In this example, the controller trained explicitly for bars shows the best performance. However, the other controllers not explicitly trained for bars also perform well in the bar environment. We further apply the controllers trained for bars in the environments containing arbitrarily shaped objects. We load in a teapot mesh and ask a user to draw arbitrary obstacles. No collision detection, no reparameterization of the environment is required, but the controllers can navigate the characters through the obstacles to the goal. In this demo, we show that we can provide interactive control for the users, and the characters can respond automatically and instantaneously to user input. Our final demonstration uses a game-like scenario to highlight the advantage of reinforcement learning over pathfinding techniques in real-time applications. In this closed environment, all the obstacles track the character, and the only goal of the character is to survive by not colliding with any obstacles or walls. Since the goal is not a concrete state or position, it is difficult to define a heuristic for pathfinding algorithms such as A*. On the contrary, the scenario can be easily defined in a reinforcement learning framework, and a surviving strategy is automatically learned by letting the character interact with the environment. Here we visualize the character's strategy. The character learns that it is important to quickly move outward through the obstacles, and then circle around the obstacles while avoiding being trapped in a corner.